Thanks, Dr. Tate, for that introduction. And thank you all for coming. My name is Kevin, and in this presentation, I'm going to give you an overview of the Capstone Project I've been working on for the last 2 semesters, as well as the various ways that Sattler has equipped me to take on this project, and also the journey I took to come up with this project and the various things I attempted and discarded along the way. Last summer, I was racking my brain trying to come up with a good capstone project that integrated the various interests that I had. And I didn't ever expect to come up with the project that I did, but here it is. So in summary, what I did for my capstone was I developed an ancient Greek sentence embedding model to be used for semantic search and paraphrase detection. I produced data sets for evaluating these various models. I developed a proof of concept semantic search tool. That's on the picture on the left there. I wrote a technical research paper. That's a picture on the second picture on the left there. That describes the technical details of the model that I developed. And don't worry about all the crazy terms at this point. I will do my best to explain them all to you in the course of this presentation. And I do apologize if it gets a bit technical. It's at some level, a bit of jargon is unavoidable, but I'll do my best to make it accessible to everybody. One of my interests for a long time now, ever since I started programming, has been computer graphics. And so when I took the independent study class 2 semesters ago, I decided, hey, I want to pursue this more. And so I developed something called a ray tracer, which is basically a way of simulating light bouncing around an environment to generate photorealistic images. And that was a lot of fun. I made a cool prototype. And I developed a capstone proposal to continue this work in the next semester. But over the summer, I realized I didn't really want to invest this much time in this project. It was a cool hobby, but I didn't want to invest myself too heavily in this area. And so I scratched my head trying to think of something else that integrated my love of biblical languages, linguistics, and ancient languages in general. But I didn't see a particular way that I could do this until I found this paper in the course of my Google searching. This paper is titled Qualitative Analysis of Semantic Language Models, and was published in the journal Ancient Manuscripts in Digital Culture. And at this point, I didn't know what a language model was, or how one could be semantic, or how you would do a qualitative analysis of a semantic language model. But I read the paper, and it introduced me to some really cool concepts like vector embeddings, word vectors, etc. And it was like, I was absolutely blown away by this, and I wanted to do something like this for my capstone. And so I quickly changed courses and started looking into this. There's nothing particularly revolutionary with the paper, but it introduced me to the whole domain of natural language processing and computational linguistics. So I dove into the world of NLP, and here is Wikipedia's definition. Natural language processing is a subfield of linguistics, computer science, and artificial intelligence concerned with the interactions between computers and human language. The goal is a computer capable of understanding the contents of documents, including the contextual nuances of the language within them. The technology can then accurately extract information and insights contained in the documents. And examples of NLP tools are, say, Google Translate, Grammarly, Siri, and ChatGPT, which is the new impressive contender on the block. And I'm going to talk about one particular application of NLP that I've been working with, which is to search documents for relevant passages based on a search query. So kind of a Google search, but much more specific. So before I dive into the specifics of my project, I want to first talk about the problem that it solves. So computers store text as sequences of characters, the letters of the alphabet, or punctuation, or whatever, emojis, whatever it may be. And so when a piece of software has a search feature, you type in something in the box, it finds a sequence of characters in the document that match what you typed in. So that's the most basic way you can do search. And this is great if you know exactly what you're looking for. But the problem is this isn't how humans think of meaning. We think in terms of concepts and meaning, not in terms of the characters used to express some thought. So imagine I'm searching some document for this phrase, Presidents of the United States before 2020. And a potentially relevant document has this phrase in it. The following people were president of the United States, or of the USA, prior to the year 2020. And if I try to do an exact text search there, nothing will come up because there's no sequence of characters that matches exactly that. if I search for keywords, so like if there's words that are contained in the search query and in the document, then of the 2020 they match, but it's not exactly capturing what I'm looking for. And there could be millions of sentences that would contain those three words. There's a more fuzzy version of this that people do where they chop off suffixes. For example, the as off of president, the plural suffix, and you get that matching. So that's a bit better, but there's a few problems. Like there's no relationship between words. They're all just discrete units, and it does not understand synonyms. So here we have prior to, which means the same thing as before 2020, but this model has no idea that prior to and before mean the same thing, and so that'll never come up in a search. And so basically, unless you know exactly the characters you're looking for, it's useless. And furthermore, going off of the synonyms idea, text-based approaches cannot detect the similarity between pairs of sentences like these. So if I say, I bought a pre-owned car, I purchased a used automobile, I went to bed early last night, yesterday I went to sleep earlier than normal, or I washed my clothes and I did my laundry. These pairs of sentences say roughly the same thing, semantically equivalent, but as far as text goes, they don't share any words. So one domain of NLP is to get computers to understand the similarity of sentences like this. So this is referred to as semantic textual similarity. The solution to this problem is embeddings. And one of the recent innovations in natural language processing is to create what we call embeddings, which are numerical representations of the semantic content of pieces of text. And so rather than characters, we want a numerical representation that we can compare. And then words and sentences that mean the same thing should have a very similar numerical representation. So in the previous slides, those pairs of sentences, if we convert them to, say, a numerical representation, if they mean the same thing, they should be very, very close. And if they mean different things, they should be far away. And of course, we can't do this manually. I can't produce this by hand because every language, including English, simply has way too many words to map this out by hand. And so the field of machine learning comes in here and helps us find these word relationships by learning them automatically from large amounts of data. So at a basic level, and by the way, embeddings can be created for any kind of media, not just text, such as images, videos, any kind of document. And you have some kind of embedding model, you feed it in, say in this case text, and out you get a vector, which is simply a sequence of numbers. Oops, sorry. So in 2013, some Google researchers came out with an algorithm called word2vec. They published this paper which kind of revolutionized the field. The word2vec algorithm learns patterns in language by learning from vast amounts of data. And it's based on the idea by this linguist in 1957 who said, you shall know a word by the company it keeps. Here's a diagram of word2vec. So it looks absolutely crazy, but it's not too bad. The idea is it scans through text, and there's a center word, which is highlighted in green. So there's this question, is this the first document? So the word the there is highlighted in green. And then there's context words around it. So usually, in this example, it's just one word, but in real life, it's like a five-word context window. And the network learns to predict the context words based on the target word. And if you do this, it readjusts all the internal network weights based on the feedback given to the model. And if you do this over billions and billions of words, it actually learns good representations. And at the end, you discard all this like prediction stuff. You just keep the internal weights of the model and use those as word embeddings. And so when you're done, you'll get something like this. So like each word in your vocabulary will have like some numbers associated with it. And it's like a black box. You don't know why it shows these numbers, only that it learned them automatically through the machine learning process. And these vectors are hundreds of dimensions. So word2vec is usually around 300 dimensions. Of course, we can't visualize this. It's absolutely ridiculous to think about. But similar words have similar vectors, and it works really well. And different dimensions probably encode different aspects of meaning. Here is a two-dimensional down projection of an English model trained on word2vec. So here's a cluster of words. You have teaspoon, teaspoonful, tablespoonful, cup, cupful, cups, tablespoons full. So it learned that these words all mean the same thing based on usage. And here's another interesting cluster. You have stir, pour, strain, stew, boil, stand, cook. Once again, it clustered those words together. It's kind of like a sanity check to see, like, is this actually working? And it does. And another cool thing is that you can do word math, which is crazy. So you take the vector for a word, and you can like add it and subtract it with other. It's just vector math. So you take the vector for king and subtract man, you add woman, and you get the vector for the word queen, or something close to it. Same with walking, minus walk plus swim gives you swimming. And you can do this for a bunch of domains, so like male and female versions, so like king and queen, man and woman, versus or like walk and walking, swim and swimming. And then country and capitals. So given enough data, so it's like these models are trained on Wikipedia, so they get a huge amount of, a huge domain of various kinds of data. And so they actually pick up the nuances of country and capitals and things like that. So clearly some amount of knowledge that is embedded in the way we use language is being captured by these models. And when I learned about this, it blew me away. I thought it was absolutely crazy. In 2019, some Google researchers once again released a new model, this one called BERT, short for Bidirectional Encoder Representations from Transformers. And this solves the one major problem with Word2Vec, and that is the Word2Vec training process produces a single vector per word, even if a word has multiple senses or meanings. The technical name for this is polysemy. So here, think of the word bank. So it can refer to a financial institution or the side of a river. So I put my money in the bank versus I sat on the riverbank. Or even in the same sentence, you could say, the bank by the riverbank keeps the money safe. And if I was to take the sentence vectors, so the word vectors of these words in the sentence, it should give me a different one based on how it's used. But Word2Vec wouldn't do that. It'd kind of be some average or something. And BERT does this, and it learns this by, instead of the technique I showed you before, where it predicts context words, BERT is trained by a lot of text is fed into the model, and 15% of the words are masked out, and the model predicts the missing word. So here it says, how are blank doing today? And it will predict like you, they, something like that. Or your wouldn't be a good one, so it would learn not to do that. And once again, doing this over a massive corpus of text, like all of Wikipedia, in like 800 million words of books, it learns really, really impressive amounts of information. However, it is much, much more complex, computationally complex. The Word2Vec one, like on my computer, I can do in like 15 minutes. On a really expensive computer, it'd take 2 days to train a BERT model on a similar, even with less data. So that's the difference there. And BERT actually, to accurately predict words, it has to actually start to understand syntax and grammar and things like that, whereas Word2Vec is purely based on word proximity, like where do words appear together. So it's much more advanced. Okay, so far I've been talking about word vectors. So now I want to produce vectors for sentences or larger sequences of text. The word sentence embedding is used in computational linguistics to refer to like an embedding for any sequence of text, not just sentences. This could be paragraphs or many paragraphs or like a book. And there are methods called pooling methods, which you can like simply average them all or take the minimum or maximum of various techniques like that can be used. And your model will then like, you feed in a sentence and it outputs just one vector for the whole sentence. However, there's different use cases for sentence vectors, and further machine learning training is done on top of these to get different desired properties. For example, you could give a question and answer pairs to learn how to answer questions, so that the question and an answer will be in similar vector space, close to each other, or just paraphrases to understand idioms, etc. And some of the best English models out there are trained on 1 billion pairs of sentences, which is massive data sets, and they get really impressive results. And once you have sentence vectors, then you can do this cool thing called semantic search. Instead of text search, you can do semantic search, search by meaning, rather than by the characters of the text you typed in. So first of all, a user types in a search query, like what color is the sky? And then the model converts that into a vector, some random numbers here. And then you compare that against all the vectors of all the sentences or chunks in the corpus you're searching. You rank them by the similarity to the query, and you just return the top like 10 or 100 or whatever. Here's a two-dimensional visualization of this. So, the query would be like hundreds of dimensions, but say in 2 dimensions, to think about this, it'll occupy some space in this vector space, and then all the relevant documents will be scattered here. You want to find the ones that are close by. So before I went on to apply all this to ancient Greek, I wanted to do a proof of concept with English to see what was possible to serve as like, in the best case scenario, what could I do with Greek? So I took the early church fathers and performed this kind of analysis on them. On the Logos Bible Software website, where they talk about the early church fathers collection, they have this to say: the Logos edition of the ECF represents more than 18,900 pages of text, 166 different authors, 2,193 individual articles or books, nearly 50,000 footnotes, and 293 editorial articles. It is one of the largest electronic reference books with complete footnotes ever produced. Okay, so now if you want to know what the early church believed about a topic, like, you're not going to mine through that. That takes way too long. So good search tools are really important for things like this. And so I thought, okay, this is a perfect test case to implement semantic search. So I took one of the really good models that are available, pre-trained with like 1 billion pairs of examples, et cetera, and applied it to this. But first, I compared it with Logos. So Logos has the early church fathers in it. As students at Sattler, we all get access to Logos Bible software for a discount during our first semester. So I told it to search for, okay, let's say I wanted to know about, like, you know, the theology of the early church regarding like the body of Christ with the bread and communion or something. So I searched for communion and bread is the body of Jesus. And it likes to match the word the and of, and it's not exactly useful. Because the early church doesn't use communion very often to refer to this, and so it doesn't have that semantic knowledge. This one's kind of relevant, but kind of by accident, because there's nothing about communion in that sentence. So I thought I could do a lot better with semantic search. So I'm going to right now show a little demo of the search tool that I built, this web tool. Here it is running. Okay, I'm going to search for the exact same phrase that I searched for in Logos. So, communion bread is the body of Jesus. Search. Okay, so here we have something from John of Damascus. The bread and wine are not merely figures of the body and blood of Christ, God forbid, but the deified body Lord himself. Okay, so he has this very high view of it. Here he talks about sacraments of the body of Christ and the bread. So like all these are like very relevant. If you're studying this topic, these will all be very relevant passages. Other things to show how this works. Even if you just type in something like hello, you got a lot of greetings, like greet all that love Lord Jesus Christ. Send greeting. I send those who are with me much greeting to you and all the brethren in Christ. So none of these say hello, but it's knowing, okay, I'm searching for greetings if I say hello. Another example is, let's say you search for Garden of Eden. Okay, the first couple mention Eden explicitly, but if you scroll down a little ways, this one, for example, it talks about the paradise and the fall in the garden, but the word Eden doesn't show up at all, but it's still ranked like fourth here. And here, for example, what was life in paradise and what was the forbidden tree? None of the words in the search query are there, pretty much, but it's totally relevant to my question, to my search query. So this is the kind of thing that makes it really useful for searching a large corpus of text where you're not sure quite what you're looking for, but you can only paraphrase your idea. Okay. Right, so from the beginning, I wanted to take NLP research and apply it to ancient Greek. And so I went and looked around, okay, what kind of data sources do I have to work with here? And you need a lot of data. The BERT model by Google was trained on like over a billion tokens of text, all of Wikipedia, and like thousands and thousands of books. The problem is there simply isn't that kind of data for ancient Greek. It doesn't exist. I found 2 online data banks that collect some text. Perseus Digital Library, actually run by Tufts University here in Boston, which is really cool. And the first 1,000 Years of Greek project, which is run by the Open Greek and Latin project. And these 2 projects together only host around 32 million. It sounds like a lot, but relatively speaking, it's not. This includes things like everything from the Greek philosophers like Aristotle and Plato, historians, Thucydides, Herodotus, Plutarch, etc. Obviously New Testament, Septuagint, and then some of the church fathers like Polycarp, Origen, Clement. So I took all of this and compiled it into one massive data set. And besides the amount of data, there's also other challenges. Like Greek has diacritics, which are little markings, breathing marks and accents that go on top of the characters. And some words only differ by diacritics. So like the preposition n, which is like in, first, which doesn't have an accent mark, and then n with a breathing mark, or hen, the number 1. And if I take those marks off, then the model needs to distinguish them without those hints. And in some cases, accents actually change. So like acute versus grave based on the next word. And sometimes the word will pick up an accent from the next word. Like the Lord's Prayer to ono masu, like the su makes the previous word have the accent. And we don't want to treat all these variants as different words because they're the same word. But if I just simply feed the data into the model, it's going to think these are all different words because the characters are different. And so I have to decide, should I keep them or should I strip them? Interestingly though, Greek was originally written without diacritics, and they were added later, like in the 2nd century AD. And so theoretically, the model, a good contextual model like BERT should be able to infer that information based on the context, if the original human readers did. So I decided to strip them for that reason. And Greek also has a lot of morphology. So as you can see here, the word grapho has like, this is just one conjugation, and here we have like 6 variants. The actual verb chart, verbs can inflect in like almost 400 different ways, which is crazy. And we don't want to treat these all as unrelated words because they all share this stem. And I want the model to capture this stem to spread its knowledge across all the different forms. But the problem is you can't just split and make a clean line because sometimes when you add a suffix or an affix, the stem changes. It's called a morphophonology or morphophonemics. There's like a bunch of words that talk about this. And so I can't do a clean cut. And so I've got to somehow deal with this. Otherwise, there's just going to be a lot of different words, a tremendous amount of different words. Or you can lemmatize the words, which is convert each word to its lemma, but then you lose all the morphological information. So for each word, just convert it to its lexical form. So a graphomen would just be grapho, or Andres would just be aner. So I took all the lemma, I lemmatized all those 32 million words of Greek, and then I did word2vec on it and to see what would happen. And I got this chart. So I got 2 interesting clusters. So here's kamelos, provaton, therion, 3 words all talking about animals. They cluster together. Here we have anthropos and aner are together there, both words to describe a man. So that was a good sign. I was doing something right. But it's not nearly as good as the English one because the data set was much smaller. Like, I don't know why machera is here. It's a sword. I don't know what that has to do with an animal. Unless people like to kill animals with them. And a really interesting development with these large language models, such as BERT, is that they can be trained on many languages at once. And some researchers at Google and Facebook have trained large models on over 100 languages. These are called MBERT and XLMR. And the cool thing is that when you train a language in one of these models that has a small amount of data available for it, it picks up knowledge from the other languages and it performs better than it would on its own, which is really cool. So I thought, hey, let's put ancient Greek into one of these models and see what happens. Especially since these models are trained on modern Greek. So modern Greek has differed significantly from ancient Greek, but it's still the most similar of all the languages in this model. It shares the same alphabet. Some historical words, especially nouns, are still the same. So I thought I would do this. And you can add a new language to a model like this without training from scratch. And so that's what I did. However, I still needed a way to produce sentence embeddings. And I didn't have this massive data set of 1 billion sentence pairs to train sentence embeddings. So I found this interesting method called knowledge distillation, which basically means you take a large model with trained on a huge data set with many, many parameters, and you condense it down and give it to a smaller model. And I use this process to transfer knowledge from an English model, so that, the state-of-the-art one from Google or Facebook, and get a student model to mimic that, but for Greek instead of English. But to do this, I needed lots of translated sentences, from Greek sentences translated to English. And here's a little diagram of how this works. So the teacher model gets the English version, and it produces a sentence embedding. I take so hello world, and then here kozme is the Greek version, which I feed into the student model, but also the English, and then it produces 2 sentence embeddings. And then I train the student to minimize the difference. MSE stands for mean squared error loss, and so I do the same thing for the English and the Greek. And when this is done, you get language agnostic sentence embeddings. So if a sentence means the same thing as another sentence in another language, they should have the same representation with an embedding. And this has a lot of cool benefits. So this means I could then do semantic search where I type in an English phrase and get Greek text back as a result. I don't have to search in Greek. So this reduces the barrier to entry for using this as a research tool. So where on earth did I get all this parallel data? Because you need a lot of it. But not nearly as much as for other methods. So 100,000-ish sentences is enough to do this, which I more than got. I got 150,000 sentences. The easiest sources to get sentences for were the New Testament and Septuagint, because these are already converted into verses. And so I just take the verses of the Greek text and the English and I'll map them together, and then that gave me like 40,000. And then the data sets I spoke about before, the Perseus and First 1,000 Years of Greek project, they have English translations for a lot of their Greek texts. And so I extracted as many as I could from these sources. And some of these sources were aligned by chapters or by smaller chunks, but not by sentence. So I had to use various sentence alignment techniques to align them by sentence. And here's an example of this. So here's the DDK, the Greek, first couple of sentences of the DDK, the Greek text with the English beside it. And this particular translator followed an approach where he pretty much did a one-to-one, like sentence-wise. So for each Greek sentence, he made one English sentence, which makes it really easy because I simply just map them over, like they're in the same order. There's not much alignment to be done. It's a one-to-one mapping. But unfortunately, Greek sentences can be really long and complex, and so often English translators will split them into multiple sentences. And in that case, I can't do this mapping. That it's not clear. How does the computer automatically know like which English sentence goes with which Greek one? Because it could be multiple in both ways, multiple Greek to multiple English, to one English, or multiple English to one Greek. So I did some research on sentence alignment methods. There is one open source tool called HunAlign that does this and uses a combination of length heuristics based on the ratio of sentence lengths to each other, and also dictionary. So if it finds sentences where it knows words line up with each other, then it can, with high confidence, know that these are translated sentences. And I generated this dictionary using the ESV reverse interlinear amongst some various other sources. And that got me up to 150,000 translated sentences. And then I trained my model with knowledge distillation, and I'll now show you a demo. Of course, if you don't know Greek well, this will be harder to. It's harder for me too. I can't always tell if what I'm searching is actually relevant. Andrew Lamasala was a really big help for me here. So I'll switch my mode to Greek here. I'll set a question. Who founded the city of Rome? Oops, I'll just delete this. And I want to search for secular sources, not church fathers, so I'm going to switch to non-Christian writers and see what comes up. All right, so here we have a result from Plutarch, who says, some say it was Romulus, son of Odysseus, who founded the city, and then others say it was, he lists a bunch of other names. So yeah, perfect answer to the question in the first result. And these other ones also do. So I think I was pretty happy with this. Not all of them work as well. It doesn't work quite as well as the English version, but it does really well in some cases. And I search for something simple like God made the world, get passages about creation. I'll switch to the church fathers again. Give me a sec here, and search. Here are things about theos, ektise, tapanta, so God creates everything, uranon, kagein, and all that. So like the heavens and the earth and all that's in them. So that's definitely relevant. And here we have Genesis 1:1, epoise no theos ton uranon katen gain, so the first verse of the Septuagint. And you can also search in Greek, so I'll show you an example. I'll show an example of a result that doesn't share any words to show that the semantic nature of this is coming through. So instead of epoisen, I'll use ektisen, which means to create. And then instead of theos for God, I'll use kurios, which means Lord. And then instead of like the heavens and the earth, like uranos and gein, I'll say cosmos. Okay, so the first result is Epuisen otheos ton uranon kete gain. So this shares no words with the search query, but it means the same thing. So I think that was a pretty good example of this. All right. Now I trained a lot of different variations, and I needed a way to see if how are these comparing with each other. And so I created some data sets with the help of Andrew to be able to compare these various models for performance, to give me a score, like a tangible, quantifiable outcome. The STS, semantic textual similarity, is a bunch of sentence pairs with a score assigned to it of between 0 and 1, how similar they are semantically. I produced a QA data set, which is questions and answers. Then also took out 2,000 sentences from the parallel data and didn't train on those. So the sentences that the model had not seen before, to see how accurately it could pick out the correct translation. So here's some examples of the sentence pairs. So like, the Stoics declare the world to be spherical. A Stoic thinks the Earth is a sphere. So it means like the same thing. So but it's slightly different because it's singular instead of plural. So that'd be like roughly a 0.9, just as an example. And then I had like hundreds of these. And so here's all the models I trained. There's a lot of, it's hard to understand. But basically, the knowledge distillation method worked the best at 87% correlation. On the translation matching accuracy task, my best model actually wasn't the knowledge distillation method, it was a different method, but it got 94%. It correctly identified 94.5% of the sentences, and the worst method got 6.78%, so big difference. And then here's the question answer. The best model got 71.35% average. Correlation. That's not like percentage of answers right, but in correlation. All right, so this was computationally very intensive. As I mentioned before, the simple models like Word2Vec can take like 10 minutes, but this took like 36 to 48 hours end to end to train just one of these. So like to populate a graph like this, that took like a week of nonstop running on a computer to produce those numbers. I used a GPU renting service called Vast.ai, which gives you cheap access to PCs, pretty good high-end hardware that I wouldn't want to buy myself. An RTX 4090 costs roughly $2,000. I didn't want to buy one just for my capstone, so instead I rented one. I rented access to one, and I used like around $300 of computing time on it. So what are the use cases for something like this? The obvious one is, so you just want to do research on the patristics or historical texts, and in the original languages, you can just do a query and like find authors and passages that talk about this topic. Even if you don't know how to phrase it, if you can roughly say what you want, you can probably find something. Another cool thing is paraphrase quotations. So if you search for a quote from, like a verse from the Septuagint in the Church Fathers, you can see where they quote it, and sometimes it's not exact. Sometimes they like paraphrase a little bit. It's pretty cool. You can find those paraphrase quotations in the Church Fathers. Or if you have a quote from the Church Fathers, let's say in the English, like, you know, Tertullian says something like, no, the blood of the martyrs is the seed of the church. Like, okay, is that how he said it? I don't know. I'll type in how I think he said it, and then if it's close enough, you'll find it. You can cluster text by similar topics to find related text, related things to each text. And then the cool thing is you can search a text that you don't have an English translation for. Like it might exist, but you don't have access to it. You can still search it with English. So once again, these are my deliverables, the embedding model, the data sets, the proof of concept search tool, which I just demoed, and then the technical research paper, a 15-page paper, which goes over this. And Sattler equipped me in various ways. So obviously computer science classes were a big deal. Biblical language classes, which gave me a passion and excitement about ancient Greek. Obviously, I wouldn't be doing this without knowing Greek, so I really love that I learned Greek here. I took a linguistics class, which was really cool. Like being excited about the nitty-gritty details of language and morphology and semantics. It was really fun for helping me with NLP. The history core and historical theology classes, like in historical theology, reading all these ancient texts was like made me interested in these and wanted to know more about them, so that was fun. And also learning how to do research in general, like where do you go? I read dozens of papers technical papers throughout this process, and getting Sattler taught me how to be accustomed to that process and know how to do it. And finally, my network of people. Dr. Tate gave some connections to me, some friends who work in the industry. That was really nice. And Seth Howell, shout out to him. He gave me some connections as well with some people around here in Boston. I even invited a Greek computational linguist type guy to come speak for us, so that was really fun. The personal impact. So yeah, reading all this research, and I learned a ton about NLP. Before I started this, it was totally new to me. I gained a lot of exposure to this world. I gained experience with Python machine learning frameworks, like PyTorch, transformers. That was really good. I found potential research topics for the future. If I'm interested in grad school, I kind of know what I want to study now. And kind of give me a vision for the future and see how machine learning can impact historical research in the future. I think tools like this are not a substitute for actually reading things, but give you a good place to start. Like, I don't want to turn this tool into a glorified quote miner, proof texter for the early church, but I want to give you a jump start in finding relevant topics. And I think this is only the beginning. The world of NLP just kind of exploded around me as I started this project with ChatGPT and similar models being released. So for better or for worse, I kind of jumped into a really active research field. There's a bunch of things I want to do in the future. I'm not going to go over these in detail, but ways I want to improve the model. I think there's a lot of future work to be done. So yeah, thanks everybody for listening. And if you have any questions, I'll be happy to attempt to answer them. Yes.
Awesome job, Tom here. I didn't get to watch the full thing, so if you already answered this, please shoot me down. I'm curious on the embedding model itself. So you mentioned like sentence embedding. If you move to like paragraph embedding or word embedding, how would that have changed the results? And is that something that you could add in at a later time?
Right. So this model works with chunks of text of various sizes. Main thing is when you train the model, you got to decide how big the maximum size is, and that affects how long it takes to train it. So you try to make it as small as you can for your use case. But there's no, in theory, there's no limit to how big it could be. In fact, here in this tool, you can see I have two modes, sentence and passage. Sentence just finds sentences that relate to your passage, to your query. But passage, it takes big chunks of text and finds a relevant result, and then it finds the most relevant sentence within that chunk. So this is better for like topical searches. This is better for like paraphrase searches.
And follow up, how does it do with direct, like if you give it a verse in scripture, how does it do finding a direct result of that, or a direct word lookup?
It's not so good with direct words. If you want to do that, the existing tools out there work great because it's just a direct text search. You can do that. But if you do like a quotation, like you can take the Greek text of like if I take the first verse of the Septuagint, oops, sorry. You'll find a ton of direct quotations. Like these are all identical to what I typed in. So you can find direct quotations. And I just scroll down. Like this is actually one, so like every single character was identical, so like 100% the same. As you scroll down, you'll see like people quote it in different ways. Interestingly, some people like mix it with John 1:1, things like that. Or they introduce the quote with like he says or something like that. We got facine in this case. Thanks for the question.
What do you want to do in the future yourself?
Right, yeah. So throughout this project, I've become really, really interested in NLP. So I'm thinking of, I'm thinking of going to grad school and studying NLP at a graduate level, and hopefully applying it to historical texts. I think that's a niche I could work in, that I could make a contribution in. So yeah, I'm really interested in doing that, as well as taking this project further. Yeah. Stan?
I I know that you and I talked about this at some point in the past, but I'm curious if you have any updates on like what it would take to get something like a tool like this into like Logos or one of the popular Bible tools.
Yeah, I mean, I would love to have this in Logos. I'm sure they're not. I'm sure they're aware of stuff like this. Like this is not exactly. I mean, it's new, but it's not unheard of. Like people are doing stuff like this everywhere. The thing, the problem is to add this into a software like Logos. This takes a lot of data storage, like gigabytes and gigabytes of space. So adding this to Logos, you'd have to figure out how to do this efficiently. So there's probably a lot of roadblocks from doing that. I'm sure it's going to pop up soon. Things like this. Yeah, Hans?
This is fantastic, first of all. I'm just mind blown that I couldn't follow most of that, but it's really great. I'm wondering, is this a public page? Can we access this and use it? Or is it going to be at some point?
Yeah, this URL, if you go this on your device, okay, you'll find this, yeah. semantic-search.kevinkrahn.com. I can send out the link afterwards.
To follow from that, do you see this page changing much, or is your future work going to be in another kind of platform?
Yeah, if I do more tweaks, I'll probably publish them here as it improves. Yeah. Oh, the URL might change as actually publish it as its own website. Currently, I own this domain, so I just added it there. I didn't want to pay for a new one. Stephen?
Yeah, thanks, Kevin. Question on the actual model, like the way you have it set up. If somebody wanted to create their own version of this, or maybe you wanted to sell it, like how are you thinking about that? Are you thinking more? Have you thought at all about how you would maybe distribute something like this? If you know what I mean.
Like to monetize it, or?
Yeah, or even just make it open source or something where, you know.
Yeah, I'm thinking of publishing the model online. There's a site called Hugging Face, which great name, but it has a ton of AI models published for free on there. I might do that. That's one way to be able to get access to it. I would also like to publish the source code on GitHub at some point. Right now it's a bit of a mess. I don't want to do it just yet, but hopefully publish the data sets and source code. Okay.
We're almost out of time. Anybody on Zoom have a question? Okay. Thank you, Kevin.